Okay, so we define what is cone. A cone with direction y is a subset of the d-dimensional Euclidean space, and aperture theta this side, where theta is between 0 to pi. So, C of y comma theta, that is the notation we are going to use, is the set of points in the d-dimensional space such that the inner product of x with y is like direction, okay, x and y, the inner product, is greater or equal to the norm of x into norm of y into cos theta. Let us understand this cone better manner. Imagine that theta is 0. If theta is 0, then cos 0 is 1. So, then Cauchy-Schwarz inequality says that this must be exactly equals to this, because this is always less than or equals to norm y, exact, and that equality happens when x and y are same. Okay. So, basically that would be just y itself, there will be no other point, the cone will be just exactly this line. But now if theta is not 0, but theta angle increases, then you are going to add more and more points, I mean, in this cy theta. So, this is a cone. Okay. A point A in the boundary of the domain is said to satisfy Zarembas cone condition. So, Zarembas is a mathematician. So, following the name of Zarembas, we call the Zarembas cone condition, because the condition these are the things which were studied by him. If there exists any particular direction y, non-zero of course, vector y non-zero, so that you can get direction, and theta, some theta between 0 to pi, such that imagine A is attached here, okay, A, and you are attaching a cone, okay, A plus C y theta. A plus C y theta would be then a cone where the vertex is A, is a subset of R d minus d, that is a subset of the complement of d. So, what is the point? The point is that we are talking about the complement, the shape of the complement of the domain. Okay. So, first example of irregular point was the complement was disconnected. One was outside the ball, another component was just the origin itself. Then second example, their complement is approaching very narrowly to the boundary, to one particular point of the boundary. Now, we are saying that okay, if we can attach a cone, theta is strictly positive, so more than 0. So, some angle, some strictly positive angle, if you can attach such type of cone on the complement of the domain, okay, then we would call that call it A satisfies Zarembas cone condition. Okay. Imagine that when surface, the boundary is very smooth, then actually you can take theta as large as say pi by 2, I mean close to pi by 2, like the full thing, okay, full one side is there. Okay. Like if your domain is a ball, then you can actually take theta is equal to say pi by 2. Okay. Now, this theorem says that this is a good thing to have Zarembas condition, because if Zarembas cone condition is true, then it is regular. As I was telling that for spherical domain, the Zarembas cone condition is cone, you can actually attach a cone of theta pi by 2, etc. The large these things, and that is smooth also. We have that understanding. However, the example what we have constructed, there we know very well that there is we cannot attach such kind of cone, because it is becoming narrow, so narrow there, no particular fixed angle can be attached there. Okay. So, if A satisfies Zarembas cone condition, then it is regular. Okay. This is the theorem. The proof is not very complicated, it is trivial actually. So, take the probability, conditional probability, the Wt touches the cone C with the direction y and aperture theta. So, we would like to find out this probability. We know that Brownian motion has is normally distributed for a fixed t. Okay. So, here we have fixed t, correct, a particular time t, and there it is in cy theta. Okay. So, to find out this probability, we need to integrate the probability density function of the normal random variable over this set cy theta, correct, to find out the probability. So, cy theta is the domain where we are integrating the probability density function for this random variable Wt. So, what is the distribution? The normal mean 0 and variance t. So, and it is in the d dimensional space, correct. So, the density appears like 1 over 2 pi t to the power d by 2 e to the power of minus norm x square by 2t. Here we get x minus mu, correct, mu if the mu is the mean, but here Brownian motion has 0 mean because w0 is equal to 0, correct. It started from 0, so it has 0 mean. So, norm x square. So, now we would take this transformation. So, z is equal to x divided by square root of t, and if you do substitute that manner, okay. So, x is a vector, z is also a vector, okay, but 1 over square root, so this is scalar. So, this scalar multiplication of that, and then if you take this del z del x, this Jacobian, okay. So, then 1 over square root of t and the identity matrix would appear here, and then del z del x inverse, if you take this just square root of t times identity matrix. And if you take determinant of that, the whole thing, then this constant would come out, but with the power, correct, because there are d number of rows. So, to the power of d, so t to the d by 2 would appear, and determinant of the identity matrix is 1. So, we are going to get t to the d by 2, but that is t to the d by 2 would also cancel with this. So, the Jacobian would appear here due to this transformation, that would cancel with this, and then x by these things would become the z. So, we are from this line we are going to get this line where t disappears totally, okay. So, it does not depend on t, we get some number, we call that q. It is of course a positive number, because if cy theta has positive measure, and that is true because theta is positive. So, it has a positive measure. So, on that this value is q, which is positive. Next, what we do is that we take the probability. So, we are going to take this probability, okay, but actual our intention was to find out the probability that sigma d is less than or equal to t, okay. What is the probability of that, okay. So, given w0 is equal to 0. So, this probability is greater or equals to that probability that wt belongs to cy theta, okay. Why is it so? Because here cy theta is in the complement of the domain, okay, is outside the domain. So, wt is in cy theta, okay. So, a belongs to a satisfies Zarembas cone condition, okay. So, that means that this is in subset of R d minus d, okay, is outside the domain, okay. So, this thing that for a particular time that sigma d is less than or equal to t, that means that Brownian motion leaves the domain at or before time t, okay, if sigma d is less than or equal to t. However, here we are just saying that wt is touching this cone, okay. This is so. I mean, this is a subset of this, correct, because this can happen in many different ways. This is only one particular way, because if this happens, surely this happens, because if wt is in that cone, that means Brownian motion already left the domain and entered into the cone, okay. And if that happens, then of course that it left before time t. So, see, this is the superset of this, okay. So, this probability is larger or equal to this probability, but this probability is already computed as q, and that implies that, okay, that probability, and this is for all t, does not depend on t. So, it does not matter what t you choose. So, sigma d is equal to 0, okay, given w0 is equal to 0 would be positive, because q is positive, correct, and it is true for all t. So, sigma d, even if you take take infimum of all possibility for which happens, the q is the probability that would always remain there. So, this would be greater than 0, positive. So, here we can again apply Blumenthal's 0-1 law to assert that this would be exactly equal to 1, okay. So, what does it mean? That this a would be I mean, here we started with 0, correct. 0 is the point we started with, okay. So, here a very particular case, here we have without loss of generality we have considered a to be 0, okay. So, here 0 is the regular point. because this probability is 1. Okay, so let us see that okay, this appears to be little strong condition, this Blumenthal's this thing, strong condition in the sense that say domain is like this, okay, and then the whole cone is on the complementary. But however, there are domains which is like which comes like this, okay. So there may not be any escape to the infinity, and we do not need that much, because what we need only local behavior. So this much that it is extend to the infinity, that thing is redundant. So this is the illustration of that. Imagine that a point is here, the far part of the domain is coming like this, which is resisting to attaching a cone in the complement, should not force A to be regular or irregular, because if A is regular or irregular, that should only depend on the local behavior of A, correct. So that is a drawback of this theorem, that the theorem statement actually does not take care of this type of examples. However, one can extend the theorem very easily. One can take a part of the domain, okay. So if this is the domain, okay, so D, and then we take a ball of radius r around A, and then we take intersection. So then this moon type like part what appears would be your new domain. So in that new domain, A is a regular point. A is a regular point. I mean, A satisfies the Blumenthal's, satisfies the Zarembas cone condition, and then you can apply that theorem to conclude that A is a regular point. Okay. So if A belongs to the boundary and there is a positive R such that A satisfies, yes, there is a type of this, A would be the script A. A satisfies cone condition for a domain which is not the full domain, but the part of the domain, okay, A plus B R, like this type of thing, then A is regular for the domain D also. So this is the remark. So we are going to stop by seeing this theorem, but the proof I am not going to start now, because it would take a long time. A full more than 1 hour lecture would be required to finish this, the proof of this theorem. So I would do that in the next lecture. The theorem statement is that the following are equivalent for a given A in the boundary of the domain. Okay. If A is in the boundary of the domain, the following 3 conditions are equivalent. First condition is saying that limit x tends to A, x being in D, expectation of f of w tau d given w0 is equal to x is equal to f of A, okay, as x tends to A. Why are these things so important? Why are, because our whole discussion is circling around this thing, correct? So because this part looks like solution of the Dirichlet problem, and this condition is saying that the solution is continuous on the closure of the domain, and unless the solution is continuous on the closure of the domain, we do not call that as a solution. Okay. And this thing is equivalent of saying that A is a regular for D. Okay. A is a regular point for D. And the third point, for all positive epsilon, limit x tends to A, x being in D, probability that tau d, this is exact exit time, is greater than epsilon given w0 is equal to x is equal to 0. So what is the interpretation of this probability? This probability is saying that if you fix epsilon, but do not change now, fix epsilon, and then you take x close to A. Where is A? A is on the boundary. When x is close to A, and then and you start your Brown motion from x, then you are checking that when the Brown motion is leaving the boundary, the time, and you are asking what is the probability that it would take at least epsilon time, at least epsilon time. Of course, if you come very close to the boundary, the probability that it would take at least epsilon time to leave would decrease, okay, would decrease. But the thing is that if it is regular, okay, then that is equivalent of saying that, okay, this would decrease to 0. So, this is very natural. So, regular thing is that what is, intuitively we understand that should happen. Okay, so those are like regular points. That is also, this is the another criteria, equivalent criteria, and this is also another equivalent thing. Okay, okay, and this would enable us to settle down for that, what is relevant for the Dirichlet problem. Thank you very much.